Greetings and welcome. Today we're starting a new chapter, new concept, and we're talking about real exponents and exponential functions. So suppose I had the equation y equals 2 to the x. All right, so not 2 times x, all right, but 2 to the x. And what does it mean to have an exponent? Could someone describe that operation? Like, for instance, if I say 2 to the third, what does that mean? Yeah, 2 multiplied by itself 3 times, or 3 factors of 2 being multiplied, whichever way you want to think about it that way. So that's what we're describing, and so that means as my x increases, I'm multiplying 2 a much greater number of times. So let's actually look at making a little table of values and kind of analyzing this situation. I might actually start up Sketchpad in the background here, or Sketchpad there. So let's plug in some numbers. What if I plug in, well actually you guys should know what happens when I plug in 0, right? What happens when I plug in 0? I'm starting towards the middle of the list, I know, but what happens when I plug in 0? 2 to the 0 is 1, because anything to the 0th power is 1. If I plug in 1, what do I get? 2, right? We get itself. Plug in 2, 2 squared. 4, 2 to the third. It's 8. Yeah, and you can see the relationship between these is this pattern is it's always double the previous term. So this would be 16. This would be 32. This would be 64, this would be 128, and then we'd have like 256, and then like 512, and then like 1024, and this is actually doubling in every situation, right? So it's just getting bigger and bigger, faster and faster. In fact, what do you think gets bigger faster? 2 to the x or x squared? We might come back to that question in a little bit. Yeah, like if you were told that you would get 2 to the x dollars, where x was the number of days of your life, or x squared dollars, where x is the number of days of your life, what would be a better deal? Interesting. And then we also happen to know that you could plug in negative numbers here. What is 2 to the negative 1? That might be some scrap work on the side. 2 to the negative 1. Let's see. 2 to the negative 1. A half. Yeah, we would move that downstairs to give it a positive exponent, and creepy homeless guy moves up top, right? The little hobbit, bam, snuck in that apartment. So it's 1/2, right? And if I plug in like negative 2, it would be 1/4, and then negative 3 would be like 1/8, 1/16, 1/32, and these would get smaller and smaller, faster and faster. Now, question: will this ever get negative? No. Right? Because, I mean, if I divide a number by 2 over and over and over, it's going to get smaller and smaller. But I can't, like, divide a positive number by 2 and suddenly get a negative number, no matter how many times I divide it by 2. Right? What is this approaching over time?
0.
It's actually approaching 0. Yeah. And this side, I think you guys agree, is approaching infinity. And it's getting there pretty quickly. Right? Let's see. So it turns out that, well, actually, you guys might know this. What happens if I plug in 2 to the square root of 2? Or, well, let me slow down. Whoa, my bad. 2 to the 1/2 power. 2 to the 1/2. So if I want to figure out what is the value of 2 somewhere between these two values, 0 and 1, that would be the square root of 2 because the denominator of the exponent becomes the index of the radical. Right, square root of 2, that's like 1.414, non-repeating decimal, going on forever, irrational number, right? And then if I wanted to say like 2 to the 1/3 power, that'd be the cubed root of 2. That decimal I do not know off the top of my head. Cubed root of 2, math, whoop-dee-doo. That's about 1.2599. So yeah, so we know that we can plug in positives. We know that we can plug in 0. We know that we can plug in negatives. We even know we can plug in rational numbers. But what if I did want to figure out what is 2 to the square root of 2 power? And that our kind of verbiage, our language breaks down a little bit. I mean, even with the fractions, it was a little bit weird. Or with the negatives, I'm multiplying 2 by itself negative 2 times, and I get a fourth. Right? The language kind of falls apart there. Multiplying 2 by itself 1/3 times. Yeah, kind of fell apart there too. And then multiplying 2 by itself the square root of 2 many times. That's kind of weird. A little bit peculiar, I might say. Don't want to close anything. So let's see. So 2 to the square root of 2, that's the same as 2 to the 1.414. What we'll end up doing is we'll estimate this using a graph. So let me actually open up a graph. Here's my graph paper. So I'm going to graph the equation. F of x is equal to 2 to the x. And actually, did we have any guesses on which grows faster, 2 to the x or x squared? Because let's see, x squared, right? Every number I plug in, I end up multiplying it by itself, right? So I mean, plugging in like 500, you'd have 500 times 500. That'd be a big number. But is that bigger than 500? 2 to the 500th power. Multiplying 2 by itself 500 times versus multiplying 500 by itself. I would think so. We might actually graph these side by side. So anyways, here is a graph of 2 to the x. So you can see that it is asymptotic. It's approaching 0. Actually, for our viewers online, let me make this show up a little bit better. There we go. Blam. All right. So so it's never negative, and it's just going off infinitely, and it gets really steep faster and faster, right? Because it's doubling every time, right? So here it's 2, and here it's 4, and here it's 8, and here it's 16, right? And it's just doubling. Let's actually compare this to a parabola, x squared. And actually, interesting stuff here. Let me actually switch to a rectangular coordinate system. Rectangular grid. And we can actually see it's a bit of a nail biter, this race between these two. Interesting stuff going on. All right, so it starts out, I mean, technically 2 to the x cheated because 2 to the 0 is 1, so it was like, it took a head start. And then around 2, they're equal to each other, right? Because 2 to the second is 4, and 2 to the second is 4. So it's a tie, like 2 seconds into the race. And then over here, it looks like the purple graph overtakes the orange graph. Peculiar. Interesting stuff. And actually, I wonder what value that is. So they're equal twice. It looks like it's around 4. 2 to the 4th is 16, and 4 squared happens to be 16. 2 to the 4th, 2 times 2 is 4, times another 2 is 8, times another 2 is 16. Yeah, so at 4 seconds, they're tied again, back and forth. But who wins out forever? I think it's the purple graph. Yeah, that just takes the lead and just keeps going forever. So, yeah, that just, no contest. And as a matter of fact, even if I, yeah, look at that. It's just like, for big numbers, it's just skyrockets. So yeah, interesting results. So you actually could have said that maybe x squared had a, like if this was a car race, oh, I just backed out of that. X squared maybe had better acceleration, but 2 to the x had maybe a quicker, it got towards its top speed faster, even though technically both of their top speeds in this situation is infinity. But, right, this one just, it was a little slower to start, and then bam, it just takes off, even though it cheated at the beginning. But, yeah, pretty good stuff. And actually, even if I made this x cubed, all right, oh, now which do you think grows faster? Looks like we've got some, yeah, it cheated at the beginning, and then x cubed, the orange graph takes over. Oh boy. Man, and then purple takes the lead again, and just like skyrockets way past it. Yeah, so 2 to the x actually will end up growing faster than any polynomial that we can think of. So exponential functions are pretty powerful things. In fact, exponential functions are used to model things like, over limited interval, they can model things like population. But eventually over time, right, like the human race is not going to continue to populate the Earth at this rate, because at some point there will just be stacks and stacks of people all over each other, and there won't be enough food. So we'd run out of space and food and other resources before that happened, right? So the limitations of your environment would take over before your population could exceed exponentially forever. But nonetheless, at least for reasonable periods of time, it can measure population. It also measures stuff like compound interest, where if you put money in the bank and you get 5% interest at the end of the year, so say I put $100 in the bank, 5% interest, I get $5 extra at the end of the year. Woohoo! But then at the end of year 2, I don't get another $5. I don't end at $110, because that would be only 5% on the 100. I'm getting 5% on the $105. So I'm getting like interest stacked on top of my previous year's interest, and it's like 105 and a quarter or something weird like that. And then over time, the third year, I'd get interest on top of even that interest, and it compounds. And at first, it might have a slow start, just like this graph here, but over time, it's actually just exponentially growing so fast that you'd have a really hard time spending it. Well, maybe you'd be creative. I mean, Bill Gates works full-time just giving his money away these days and still isn't successful. So, yeah. But in fact, Albert Einstein is quoted as saying that compound interest is the most powerful force in the universe. That's what he'd said. Just because the way that it grows is ridiculous. All right? So, that's one of the things we'll end up looking at is investing. Another thing that compound interest exponential functions are used for is exponential growth and exponential decay. So growth are things like population, compound interest. Decay would be things like radiometric dating, right? Carbon-14, where like considering half-lives of things, they can try to estimate out how long someone's been dead or something like that, based off, if it's at least been for number of years, based on the number of carbon-14 left in their body, and it ends up being a curve kind of in the negative direction. But anyways, I think I'm getting ahead of myself. Looking at this curve, let's say I did want to figure out what is 2 to the square root of 2. Okay? I want to figure out what is 2 to the square root of 2. And I could actually estimate that. Let's see. Let me actually switch over to my pen. So if I want to plug in the square root of 2 We know that this curve exists for all whole numbers like 2 and 1. And we know it exists for 0. We know it plugs in for -1. We know that it exists for things like a half or a third. But does it exist for the square root of 2? And it turns out that it does. And we can actually even estimate it off of this. So here's 1.5. Its height seems to be a little bit below 3. Actually, ooh, I wonder if I could. Could I? May I? Perhaps I shall. Here we go. Well, let me construct a parallel line and construct a perpendicular line. Bam. So you can now kind of see that as this slides along the curve, I can see how high it is over here and how over it is over here. So here's at 1.5. It appears to be at like, I don't know, what do you want to call that? 2.8-ish, right? But if I want to figure out 1.414, I just have to slide it like maybe right here. So I'm guessing maybe like 2.7-ish or maybe 6, 8 something is what I'd be able to do. And actually, I think I could even measure the coordinates. Actually, I wonder if I can do value of point at some point. So yeah, oh wow. I was close. 1.44, not 414. There we go. Apparently I get, about 2.66 for the value of when I plug in the square root of 2. All right, so it turns out I can actually do this. So these are smooth curves. They're continuous. They exist for all inputs. The domain is x is everything. All right. However, looking at the graph once again, as we're kind of analyzing this. Oh, let's see. There we go. What do you guys think? Whoa. What about the range for this function? What is the range? What's the limit of my y values? Actually, that's funny. It just rounds it to 0. That's kind of funny. What's the limit of my y values? What's the range? Yep. And can it ever equal a negative? No. So the range would be y is, or 0 is less than y, which is less than or equal to infinity, or less than infinity, I guess, technically. Right, so everything positive, essentially, is the range. So stuff like that. So it does, in fact, exist in all of those cases. So this, I think, what did we say? It was like 2.66-ish, something like that. I also, I believe, can plug in to my calculator. Let's set focus. 2 to the square root of 2. And is it focusing? There we go. So 2 to the square root of 2 is 2.665144143. So there's a decimal approximation of it. Stuff like that. Good times, good times. All right. So, yeah. So it turns out you can have real exponents, meaning we're not just limited to rational or integer or negative or positive or 0. You can plug in all sorts of crazy stuff as well. Now, let's talk about an exponential function. Actually, you know what? I might even just snapshot this right out of the Libro. So here's exponential function. We'll talk about this. And so let's see. And I guess I should label this. This is def of exponential function. Yeah. Function. Let me see if I can open up. While you guys are working, let's see, I'm going to move this and close. Don't save. And while you're writing, I'm going to be opening up another window. Let's see if I can find my Geometer's Sketchpad file. Exponential polynomial vertex form amplitude. Where would that be? Where am I hiding it? parametric, polar, exponential functions. Here we are. So, exponential function, an equation of the form y equals a times b to the x. Notice that the exponent does not apply to the a. All right, a's exponent is 1. All right, so a times b to the x, where a is not equal to 0, because if a was 0, then y would just equal 0. It would not be very interesting. Just be a flat line. And where b is greater than 0, so we plug in positive values for b. Actually, let's consider for a moment, why would that be the case? What happens if I, let's say I plugged in negative 2 to the x, negative 2 parentheses to the x. What is negative 2 parentheses squared? 4. What is negative 2 parentheses cubed? Negative 8. Negative 2 parentheses to the 4th. Positive 16. Negative 2 parentheses to the 5th would be negative 32. The problem would be that its sign would be just like bouncing all over the place. It'd be like sometimes it's positive, sometimes it's negative, sometimes it's positive, and it just wouldn't be a very good-looking function. It would not be a smooth curve, for sure. So yeah, there's issues when b is negative. And we also said b cannot equal 1. If b was 1, what is 1 to the xth power? What would that be for any value of x? 1. That would just be 1 all the time. And once again, I'd end up with a horizontal line, which would not be very interesting. And this is called an exponential function with base b. So check this out. I think I've got this up and running. So here's my little graph of some exponential functions. And there we are. So the dotted line here is y equals 1 times 2 to the x. That's the graph that we looked at a moment ago. And I just want us to do a little bit of an analysis of what happens when I change a and b. So let's change b. So if b is 3-ish, I'll call that 3-ish. Fine, that's fine. Just leave it. 3-ish, 0.11 is ish from now on, just so you know. Notice what happens. So when I plug in 1, I'd get 3-ish. When I plug in 2, I'd get 3-ish squared, which is 9. When I plug in 3, I'd get 3-ish to the third, which is 27. And then what happens over here to the left, so even though this is greater than 2 to the x for all values positive, it turns out it's less than 2 to the x for all values negative. Because when I plug in negative 1, I'd get 1/3. When I plug in negative 2, I'd get 1/9. When I plug in negative 3, I'd get 1/27. And those are less than 1/2, 1/4, and 1/8. So it turns out the curve is always less than it for values less than 1, or 0, sorry. So kind of some interesting results there. So I can plug in kind of all sorts of different values, and it gets steeper, and that affects kind of the growth rate. All right. And then what happens when I plug in something less than 1, do you think? Less than 2? It'd just be less steep. Whoa. 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 These are what I call Gumby arms, where it's just like, I don't know, going back and forth. Boing, 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 boing. Right, so if I plug in something less than 1, let's consider what's happening here. So 0.5, man, it just landed on it. Perfect. Hey! Victory. Think about this. 0.5 to the 0th power is 1. 0.5 to the first power is 1/2. 0.5 squared is 1/4, is 1/8, is a 16th, is a 32nd. Right? So raising 1/2 to those powers, it just kind of flip-flops it a little bit. 0.5 to the negative 1, or 1/2 to the negative 1. Let me write some of that down. 1/2 to the negative 1. What would happen in that situation? I'd get 1 to the negative 1 over 2 to the negative 1. It'd be 2 to the 1 over 1 to the 1, which is 2, right? It's like those guys are just like, let's switch apartments, and then they did, right? So yeah, so that's equal to 2. 0.5 to the negative 2 would equal 4, right? So this actually, a fraction plugged in for b will end up kind of flipping it over the y-axis a little bit. And then, you know, I plug in different values for that, and I can get some different things there as well. And then, like I said a moment ago, I can't plug in negatives. We broke Gumby's arms, right? It's like, yeah, 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 and then, he just, like, vaporized. Terrible news. I'm sorry, Gumby. So yeah, so interesting results. Let me see if I can get this back close to 2. 1.98. I'm just going to settle. So let's see what happens when I change the value of a. Here I've had a about 1. When I increase a, what else is this changing? Now this is a little bit harder to tell. Oh, interesting stuff happening there too. So when a is 1, it's just the regular 2 to the x stuff. But when a is greater than 1, so for instance, what happens when a is 3-ish? What else changed on us? Yeah, it's tripled the y value for all of these. And also notice the y-intercept changed, right? Because anything to the 0 is 1, we said. But now I'm taking anything to the 0 and getting 1 and then multiplying by 3. So that's going to be 3. And notice if I actually even change the value of b, it's stuck. That's the y-intercept. All right, so a affects the y-intercept. But it also ends up just tripling the y values for all of these. So notice what happened originally. 2 to the first was 2. Now it's 6. 2 to the second was 4. 4 times 3 is 12 is where that would land if I had this lined up nicely. Close enough, right? 12. 2 to the third is 8. So 3 times 8 would have been 24. So it just tripled the y values for all of these is what ended up happening. So that's what a does, is it kind of...
Ethan Beatty, please come to the school office. Ethan Beatty to the office, please.
Right, so it increases the y-intercept, and it just triples the height or multiplies the height by 6 or whatever. And then when a is 1, let's see if I can get it to be 1. It's the regular graph. And when a is less than that, it halves the height of everything or whatever. But if a is 0, I don't think I can actually land it on 0 exactly. But if a was 0, it would just be 0 times whatever this is, which is 0. And it would just be a straight horizontal line all the time. This is clearly rounded to be 0. And then when a is negative, look what happens there. It flips it over the x-axis. So some interesante results. So I'm going to have you guys, tonight you'll end up doing some problems where you'll try plugging in some different values here. We would make a table of values and plot those points and just try to figure out where our graph is. So numbers that I'd recommend plugging in are like -2 to +2, right? -2, -1, 0, 1, 2. So just plug in 5 points and then you could, see what your graph is and what's going on from there. But I wanted to give you kind of a general overview of what happens. So a changes, can flip it upside down, and b changes left to right. Let's see. So, if I have a fractional value there and negative, I can even flip it over there a little bit. Interesting stuff. Peculiar. Yes. So now that real exponents exist, it's something that can happen. Let's talk about simplifying some problems with real exponents, and then I want to actually talk about solving some equations real quick. So what if I said simplify? And what if I had, I'll say 5 to the square root of 2, all to the square root of, let's say, 10. So it turns out all other properties of exponents still apply, right? So I can have irrational numbers as exponents, and they behave the same way as the other ones did. What property of exponents do I do here? What do I do? What do I do? Do I add, multiply, subtract, divide those exponents? What do I do? Power to a power rule, I would multiply. So that'd be the square root of 20. But now I can actually simplify that radical as well. So that is 5 to the, let's see, is there a perfect square that goes into 20? 4, and it goes in 5 times. So that's 5 to the 2 square roots of 5. Which, if I wanted, I could kind of do this property in reverse, where I could say that's the same as 5 squared to the square root of 5, right? Normally you wouldn't have to write that out. And what's 5 squared? 25 to the square root of 5. All right, so I just want to point out that you can simplify some of these equations. All right, expressions, rather. You can also have stuff, I suppose, like this. What if I had 3 to the 2 square roots of 3 times 3, actually, times 9, how about? Yes, yes. 9 to the, let's do 3 square roots of 3. Now, can I add those exponents in the way they are? What's the issue?
With different indexes?
Well, the indexes are technically the little squares, but I can't add the exponents until I have the same bases. So 3 to the 2 square roots of 3 times 9, I can actually rewrite as a power of 3. What is 9 the same as?
3 squared.
3 squared to the 2 square roots of 3, right? Nope, 3 square roots of 3, sorry. And now I've got power to a power property, so I can multiply those. So 2 times 3 square roots of 3 is what? 6 square roots of 3. And now I'm multiplying two things of the same base. So I would add the exponents. So 2 square roots of 3 plus 6 square roots of 3. And because the indexes and the radicands match, that's just add them up like terms. So that's 8 square roots of 3. And if I wanted, I could actually figure out what 3 to the 8th is. That might be large, but not so large. That's equal to 6561 to the square root of 3. If we were wondering. So good stuff. Good stuff. So that's simplifying. Let's talk about solving as our last type of problem. What if I had the following? Solve. And what if I had this? What if it said 7 to the x equals 7 to the 4th? And I asked you to solve that. What would you think? X equals 4, right? Perfect, right? I mean, 7 to what power is equal to 7 to the 4th? I mean, this couldn't be 3, or 7, or 10, or pi. There's only one number that's going to be true for, and that's when x is equal to 4. So it turns out, when you have two powers that are the same, two powers that are equal, and their bases are the same, then their exponents must also be the same. And that's actually summarized right here. I'm going to snapshot this. This is the property of equality of exponential functions. You don't need to know the name of that, though. So suppose b is a positive number other than 1, then b to the x sub 1 equals b to the x sub 2, if and only if x sub 1 equals x sub 2. Right? So, like you said earlier, x had to equal 4. That's the only thing it could be. No other thing would work.
What is this definition of?
This is property of equality for exponential functions. I guess I'll name it. Of equality. For expo functions. Expo func. Right? If you've got two powers that are equal and their bases are the same, then their exponents must also be the same. And now, of course, the first thing I'm going to do is mess this up. So if I have 2 to the x equals 16 to the second, the problem here, of course, is that the bases are no longer the same. However, I coincidentally gave us a problem in which they can be written as the same thing. I believe I can rewrite 16 as 2 to some power. 2 to what power is 16? 2 to the 4th. So 2 to the x equals 2 to the... Do I add or multiply those? Multiply, power to a power property, so that's 8. And then using this property, therefore x equals 8. So that's the only thing it could have been. So sometimes it requires just some manipulation of, can I write these both in terms of the same power? And let's see, in the last example, challenge problem, what if I have 1/3 to the 2x plus 1 equals, what if I've got 27? Oh, 9, let's make it. 9 to the x minus 5. So 1/3 and 9 are not the same. So that's our issue. However, can they be written in terms of the same base? Can they be written in terms of the same base? Those are both powers of what number? 3. So 3 to the what is equal to 1/3. And 3 to the what is 9. -1 would flip that upside down and make it 1/3. And 3 to what power is 9? 2, right? And now I've got to be careful here. What do I do with these exponents? Multiply them. So -1 multiplied by this whole thing, I'm going to have to distribute it. And 2 times this whole thing, all right, I have to distribute that. That's a place where sometimes students forget to distribute. So that's 3 to the -2x minus 1 equals 3 to the positive 2x minus 10. So what must be true? We've got two powers that are the same. Their bases are the same. So therefore, what must also be the same? The exponents. So -2x minus 1 equals 2x minus 10.
Mr. Ryan, on the distribution step,
Yep.
do you only distribute to the exponents?
Yes, because it's power to a power, so I'm technically multiplying these things. And that's why I have to take very special precaution. Because this whole thing was an exponent, you know, so that's why I had to multiply to both. And now I could solve for x, bring the x's together, and I would get -1 equals 4x minus 10. And keep solving at 10. Almost done. So I'll get 9 equals 4x. And divide by 4. So x is equal to 9/4. Voila. And technically we could do a check on this if we wanted by plugging in 9/4 into both of these locations. And oddly enough, they would work. It would work. So good stuff. So yeah, the subtleties there are usually in, can you rewrite those both in terms of the same base? And that's currently our only technique for solving these. Although, if only there was a way to solve a problem, I guess this will be my foreshadowing. What if I wanted to solve this problem? 2 to the x equals 3 to the 5th. And this will be the challenge for tomorrow. Whoa, what? Can it be done? Can it be done? Well, anyways, bye, Internet. Goodbye.